Continuing the 7.1, 7.2 section. So last video for this section, these two combined sections, exponential order alpha. So we say that a function f of t is of exponential order alpha if there exist positive constants t and m such that the absolute value of t is less than or equal to m times e to the alpha t for all t greater than some big T, some value big T. Now what this means is that it could be that for values less than big T, this inequality may not be satisfied, but after a certain level or a certain value, it shall be satisfied. It means this value over here will be greater than the value on the left. So in other words, in the graph of, if you plot the graph of this side, should come above the graph of the f of t, absolute value of f of t. Okay, so here is an example of a function which is of exponential order, and the alpha here is 5 and m is 1. Now when you are asked a question whether a function is of exponential order or not, so you may just check whether there is an alpha such that e to the alpha t is bigger than the value that we are looking at, and or the function. And so we will see how we do the examples. But here we are looking at the absolute value of e to the 5t times sine of 2t. Now sine of 2t, remember the absolute value of sine 2t is less than 1, is between 0 and 1 or equal to 1 maximum, because that's the highest value sine of 2t can have. So which means this quantity here will be less than or equal to e to the 5t. So we can say that this function is of exponential order alpha, which is equal to 5, and we are taking m to be 1 here. Now condition for existence, this becomes a condition for existence of the transform. So it will say if f of t is piecewise continuous on 0 to infinity and of exponential order alpha, then the Laplace transform will exist for s greater than alpha. So now look at an example. It says which of the following functions are of exponential order. So we just have to say yes or no. We don't need to find the alpha. So we will do it in a slightly different way. So what we want to do is, so we have this function t to the 5 cosine of t. So we will divide it by e to the something t. So we have to fill this blank and t, and now we will take the limit as t goes to infinity. So and we want this limit to be 0. If we can show that, then whatever number I put in this blank space, that will be the alpha we need. So let's try with 1. Because you know that cosine of t, the maximum value it can have is 1. So so basically the integral, the dominant terms are t to the 5 over e to the t, if we put a 1 there. So, and you know that this the limit as t goes to infinity by using the L'Hopital rule will take us to 0. Now for what value of t, well, that is something we can work through, but the question didn't ask, so I'm going to just leave it. So we say that yes, this is of order this is of exponential order. Looking at the next example, we do the same thing. So we have limit as t goes to infinity, e raised to t square divided by e raised to something times t. Now what will that something be? Well, you can see if I put anything 2t or 3t, the t square is going to lead that. So this value will be way higher than the value I have here, whatever alpha I put there. Okay, so this no number, we wanted it to be 0. Okay, so no number makes it 0. So no number here can make the limit 0. So no, this is not of exponential order. So which means its Laplace transform does not exist. The next is t ln of t. And e to the something times t. So what is that something? Actually, again, we can just try the e to the t. You will see that we just take limit t ln of t e to the t. So then limit as t goes to infinity. So this will eventually go to 0 by using the L'Hopital rule. So this is of order of exponential order. So this is how we check the exponential orders. So now we will go to, in the next video, that will be section 7.3.